Hello, everybody in Living Earth. I just wanted to preface this first notes presentation that you guys are going to watch from me by explaining and making sure that everybody's on the same page. So while I go through this notes presentation, your job is to be on this over here, this note sheet that has a bunch of blanks in it. And as I go through, you'll figure out what words go in these blanks because it's going to be filled in for you on that presentation. And then you'll be able to fill that in on the copy that you made of this note sheet and upload the finished product to Canvas. So let's get started. Today, I'm going to be talking about experimental design and how to graph. Both of those things are things that we're going to use a lot in my class, so it's really, really important that you know how to do them with accuracy, and they are not going to go away in future science classes. Those things are always going to stay with you. So first, I want to start by just defining an experiment in general. And an experiment is a scientific procedure that is undertaken to make a discovery, test a hypothesis, or demonstrate a known fact. But you can do an experiment on pretty much anything you want. It's not constrained to only super specific things in science. You can do it on pretty much anything. And so for those of you that have seen Mythbusters, I included this image, which is a quote by Adam Savage, who you see in the picture. And he said, "Remember, kids, the only difference between screwing around in science is writing it down," which is, it sounds bad, but that's honestly very, very accurate because a lot of scientists, they do experiments just to see what will happen. And the only difference between some rando doing it in their backyard and a scientist is that scientists are taking data. They are forming conclusions with that experiment. They're not just doing it because. So how do you even design an experiment? Well, first you need a problem or a question that you want to answer, or something that you might be wondering about, or something you want to demonstrate to somebody else. Now this last one, that's me pretty much. I'm going to be doing a bunch of experiments because I want to demonstrate principles to you guys. But if you became a scientist after college, and you would fall more into these categories of problem solving, question answering, something you might be wondering about just in whatever research lab you may or may not happen to be in at the time. You also need a hypothesis. Now, the dictionary definition of a hypothesis is this first bullet point over here, and it is a proposed explanation made on the basis of limited evidence as a starting point for further investigation, and that is such a mouthful. But to summarize, it's an educated guess. You're gonna do an experiment, you make a guess as to what you think is going to happen. And if you're questioning yourself going, well, why do I need to make a guess? It's because when you make your hypothesis, you are trying to either prove something or disprove something. You're not just doing an experiment to see what'll happen if you mix two chemicals together. You're doing something with a purpose. So, like I said, it's an educated guess, but you need to explain what you expect to happen in your experiment, in your hypothesis. Your hypothesis has to be clear and understandable. It has to be testable and measurable, which is super, super important. You guys, if you come up with a hypothesis that you cannot test, I will tell you to turn around and try again. And the last thing is that hypothesis has to contain an independent and a dependent variable, which I'll explain in a second. But just going back to the testability and measurability, your hypothesis needs to be able to be tested. It can't just be an opinion. It can't be, I think lemons are cool. There's no way to test that. That doesn't make any sense. And if you're confused right now about what qualifies as testable or what doesn't qualify as testable, that will organically make itself clear to you within each experiment that we do or each experiment that you see happening. Okay, so independent variables versus dependent variables are very important to understand. That's why I highlighted them. It says key terms in big letters. Let's talk about an example, and I'm going to come back to this example a few times in this presentation, but let's pretend for a second that we wanted to do an experiment on different soil types and how they affect plant growth. Your independent variable in that experiment is your variable that is changed by the researcher, by you. And you are trying to see what effect it has on something else. So in this example that I just gave you, if we're testing the effect of soil type on plant growth, soil type would be our independent variable because that's what we have control over. We could put a plant in potting soil. We could put a plant in random dirt you found outside. We could put a plant in gravel. We could put a plant in sand. That's what we're changing on purpose to test its effect. Your dependent variable, on the other hand, is usually the thing that you measure at the end. Your dependent variable is directly affected by your independent variable. But another way to refer to your dependent variable is your results, because you measure your results, and that is what your dependent variable is. It is the thing that you are measuring. So let's pretend that this generic graph over here, we have soil type 1, soil type 2, soil type 3, soil type 4, soil type 5, and 6, and each of those soil types produced slightly bigger plants, which means that in this graph, your soil type is your independent variable, which always is going to have to go on your horizontal x-axis, and your dependent variable of plant growth, or the height, is going to go on your vertical y-axis. So over here in orange, I highlighted you may only test one independent variable at a time in any experiment, and this is absolutely true. You may be asking yourself, Ms. Seiler, you just listed like 7 different types of soil. Isn't that 7 different types of independent variables? No. An independent variable is one thing that you might test. So in this instance, we're testing soil type. That's our one thing that we're testing. Now we can have different types of soil, obviously sand, soil, gravel, regular random dirt, whatever. But what you cannot do is you cannot test soil type and amount of water and amount of sunlight and placement in a house and a bunch of other things together. Because if you want to know something about soil type and you throw in all these other external variables, they're going to screw up your data. And that's what I mean by you may only test one thing at a time. Okay? Another thing to be aware of is control groups versus experimental groups. Those are all categories of testable groups. So generally in an experiment, you will have a control group and you will have one or more experimental groups. So I gave you another example here on the right. We have our control group here and our experimental group down here. Now a control group is a group that does not receive whatever independent variable is being tested. So it is the standard for which you compare everything else to. And your experimental group, which is this group down here, is going to be the group of subjects that are exposed to the independent variable. So in this example, we see our control group, there's a group of kids studying or working. And our experimental group is still a group of kids studying or working, but now we've added in this variable of a band playing, presumably very loudly. So if I were to look at this experiment and try to make a guess as to what they were testing, I would say they're probably testing the effect of a really loud band on students' study habits or their work efficiency or something like that. But if I just stuck a loud band in front of you and I'd never seen you work before, I would not know what your normal work habits are to compare the new data to. So that's why it's super important that you have a control group, because you need a point of comparison. You need a starting place so that you can measure what changed. Constants are the last portion of experiments that I'm going to define for you. And constants are factors that the experimenter keeps the same across all testable groups so that that doesn't affect your data or your results. So in this dirt experiment that I've been talking about, we have multiple different types of dirt, but we want to make sure that nothing else is interfering with our experimental data. So if we're testing 1, 2, 3, 4, 5 different types of dirt, we want to make sure that each of those plants gets the exact same amount of water. We want to make sure that each of those plants gets the exact same amount of sunlight, the that the plant is even the same plant, because if you use different plants, that's going to affect your data. So we do that so that we know that our data is worth something, because if you have all of these other factors influencing your results, then your data is worthless. So one thing to pay attention to, though, is that constants are often said to be controlled for or referred to as controlled variables. That's not the same thing as the control group. And I've seen people make this error so many times. They think that myself or somebody else is talking about the control group, and we're not. You control for your constants to make sure that they don't affect your experiment. So controlled variables, or things that are controlled for, are not the same thing as the control group. And that is something that you do need to remember. So I'm gonna go ahead and switch over to YouTube for a second, because we're gonna watch part of this video and then we're gonna go through a couple of things. Oh, look, there's an
Well, first I just thought that they were
ad
freckles. Very unattractive blob things on my face.
Makes me feel like a Dalmatian.
Small.
There we go.
What is a controlled experiment, and why would you want to do one? Maybe you have an idea that you think might explain a situation. This is called a scientific hypothesis. How could you find out if your hypothesis is correct? Well, you'd set up a controlled experiment in which you control or keep constant all the factors known as variables, except for the one you want to test. Let's design a controlled experiment to test a fertilizer which claims it makes plants grow bigger, lusher, and perhaps produce more flowers, fruit, or vegetables. If you wanted to see if the fertilizer works, how would you set up a controlled experiment to test this claim? First, you would get two plants of the same species. Let's call them plant A and plant B. Everything about the plants should be exactly the same, including their size, health, and age. Next, you would put each plant in identical pots with the same amount of the same kind of dirt or soil. You would water them both the same amount at the same times. You would also put the plants next to each other in the same place, such as a windowsill, so that they're both exposed to the same amount of sunlight and kept at the same temperature. It's important that everything is the same, because the purpose of your experiment is to find out whether or not the fertilizer works. So, what would be different? In this experiment, the only difference is that only plant A would get the fertilizer. Now remember, your hypothesis is that plant A, which is getting fertilizer, will grow bigger compared to plant B, which isn't getting any fertilizer. How would you know whether your hypothesis is correct? You'd know because you'd regularly measure the plants during the course of the experiment. For example, once a week for a period of 3 months. You would record these measurements throughout the experiment. These measurements are your data. At the end of the experiment, you would look at your data and compare the measurements of plant A, which got fertilizer, to plant B, which didn't get fertilizer.
All right, so I'm going to pause it there because that's the gist of this video. We're going to go back to the presentation and we are going to go through analyzing this experiment together. So the first thing when you are designing an experiment, and obviously right now this experiment was designed for you, but we're going to title it, we're going to fill out the hypothesis, we're going to just fill out all the important bits so that you guys can identify what is what in various experiments. So the title needs to be generally something that just really quickly explains what the experiment is about. So if I were going to title this experiment, I would title it The Effect of Fertilizer on Plant Growth. It's short, sweet, to the point. Next, you need a hypothesis, and a hypothesis is generally an if-then statement. It doesn't have to be, but that makes it much easier for whomever is writing it to get all the necessary portions. If this happens, then that happens. So in this case, if plants are given fertilizer, then they will grow bigger. And you'll notice that that's different than the hypothesis that they had in the video, but that's okay, because not all hypotheses need to be the same. You could have even hypothesized the exact opposite. If plants are given fertilizer, then they will not grow bigger, which is okay to have as a hypothesis, even though clearly, given this data, that would be false. But just because your hypothesis is wrong, that doesn't mean you failed. It just means you've gotten data that disproved what your initial guess was. Next, we're going to go ahead and define our independent variable, our dependent variable, our control group, and our experimental group. So remember, the independent variable is the thing that the researcher has control over, that they are changing on purpose. So in this case, the researcher gave one plant fertilizer and did not give the other plant fertilizer on purpose. So that means that the independent variable is fertilizer. The dependent variable is the thing that is measured at the end. So they were measuring the plant growth or the plant height. So that would be our dependent variable, the amount that the plant grew. Our control group is the group that does not receive the independent variable. And if you were paying attention in the video, you would know that that was plant B that did not get any fertilizer, which means that the experimental group has to be plant A because it did get that independent variable of fertilizer. Constants is the last thing that we need to talk about for this particular experiment. And you could go on for hours listing certain things that are constants that are controlled for, but we're just going to list a few of them. Like, for example, the amount of water. So each plant was given the same amount of water. Each plant was given the same amount of sunlight. The type of dirt was the same between plant A and plant B. Plant A and plant B were the same type of plant, which is super important. So again, there are many of them, like the same type of pot was used for both plants, but those are the ones that are the most important. Graphing experimental data is the next thing that I want to talk about, and it's super important because graphs are used to demonstrate relationships between variables. I just spent 10 minutes talking about independent variables versus dependent variables. So we use graphs to showcase our data from experiments. Now, we're going to use these three graphs the most in my class: line graphs, scatter plots, and bar charts. One thing you need to understand about these graphs is that line graphs and scatter plots, that's these two, are mostly used for numerical data. And that is data that is measured with numbers, which it sounds kind of silly that I would have to say that, but I see students make that error a lot. I see them trying to do a bar chart for data that doesn't make sense to do a bar chart, or trying to do categorical data in a line graph, which again doesn't make sense. So to give you an example, if I was measuring the weights of different lab mice, I would use a line graph for that. Like over time, if I wanted to see if a mouse got bigger, I would measure that data and I would showcase that data in a line graph or maybe a scatter plot. But that's not really going to make sense in a bar chart. You're not going to have 7 different bars saying how big a mouse was at any given time. Bar graphs are used for categorical data. So like if you were taking a poll of your friends to see if they thought that lime flavoring or coconut flavoring was better, you might use a bar chart for that, because you're going to count, well, how many of your friends like lime flavoring versus how many of your friends liked coconut flavoring. And I know that how many is a number, but lime versus coconut is not a number. So that would be the categories, lime or coconut here, and that's why you would use a bar chart. And I'm sure some of you are listening and going, I'm never going to be able to tell the difference, I don't understand, and that's fine, because you're going to learn this as we go. You're going to learn to identify the type of graph that you need to use as we go. And if you have questions, I will answer them. But you also need to know how to make a good graph. I get lots of terrible, terrible graphs, and I just wanted to make sure that you guys knew what I was expecting from you and your graphs. Every good graph needs a title, which you'll see in this example up here. The title should tell me what that graph is about. I do not want you to title the graph super cool graph, because that tells me nothing. Your graph needs an appropriate and even scale. So you'll see the scale here, and you'll see the scale down here. So in this case, we've got number of organisms as our scale on the left. So we know it's an appropriate scale because do you see how these lines fill up most of the space within the graph? It's not super tiny and smushed in its corner. It's not running off the edge of the graph over here. If you had a data point that your largest data point was like 3,000, but your graph cut off at 200, I would question the appropriateness of your scale. So you have to make sure that all of your data fits on your graph appropriately. The scale needs to be even, and what I mean by that is it doesn't jump from 40 to 45 to 70 to 120 to 121 to whatever. So your scale should be even as this one's is. The axes, and that is X and Y, this one's Y, down here we have X, they need to be labeled. Because if they are not labeled, I don't know what your graph is about. I don't know which data is where, and I can't read it effectively. So you make sure that you have those labels. If there's more than one line on your graph, like this one has a red line and a blue line, you need a key, and that's what this is over here. Because if this weren't here, I wouldn't know what the red line was, and I wouldn't know what the blue line was. But this key tells me, okay, blue is rabbits, red is wolves. And suddenly your graph makes 100 times more sense. And last but not least, your graph needs to be neat and readable. If I can't read it, I will give it back to you and tell you to do it again. Here's a bad example of a graph. I have received so many graphs that are very similar to this. This scale is not even. The scale is not even labeled. Time is in the wrong place. Time never goes on the y-axis because time is never a dependent variable. Time is. So that is always going to go on the x-axis. The graph is tiny and smushed in the corner, so the scale, whatever it was inappropriate. Organisms over time, organisms where, like, I don't know. So if I had received this graph, I would have given it a 0 because this tells me absolutely nothing. However, take that same data and you add a little bit more detail, then suddenly the graph becomes a million times better. In this case, I have axis labels. I now know that the time that we're measuring is in years and I know which years. Look how even my scale is. I know that this is number of organisms and I know how many. The graph uses its space effectively. No, I don't have a key, but again, I didn't need one because I'm just counting number of organisms, so I didn't need to re-specify that over here, but I do have a title that explains what the graph is about. Is this graph perfect? No, absolutely not. But would I give it a fair score now because of all that detail that was added? Yes. One last thing that I want to make sure to talk about before the end of this presentation is that your independent variable always goes on your x-axis, and your dependent variable always goes on your y-axis. So you can see that in this generic graph here. Independent, always x. Time is generally an independent variable, so that's why time, I said before, always goes on your x-axis. It's just where it belongs. Your dependent variable always goes on your y-axis, your vertical axis. The only thing about this graph that you would not need to pay attention to is this equation right here. We're not going to be doing any experiments that require you to form an equation with your data points, so I wouldn't worry about that. But it does have all of the other things that graphs need. It has labels, it has an even scale, it has a title, it has all of those things. So this is a good example of a generic graph. All right.